So it's my great pleasure to introduce my friend and colleague, James Tanton. And he really probably needs no introduction to most of you. He's an amazing all-round guy and wonderful mathematician and promoter of mathematics joy. And he's normally traveling all around the world doing all kinds of professional development for teachers and talks for students and general audiences. And so James has been involved in math teacher circles and math circles for years and years. He is the mathematician at large for the Mathematical Association of America. He's a co-founder of the Global Math Project. He recently, this year actually, was awarded the Joint Policy Board of Mathematics Communicator Award. And anyway, it's my great pleasure to invite James up to the stage to start your talk.
Hello. Hopefully I've got my mic off and my camera on. Does it seem like everyone can see me?
Yeah.
Excellent.
I think so.
Well, hello. Welcome. What a pleasure to be here for the final hour of a spectacular week. Oh my goodness. Thank you, Aim, for putting this together. I hear it's been spectacular. I've been flitting in and out. I wish I could do more flitting in than I did out this week, but it's been mighty grand from what I've seen. So it's good to see you all. Good to see you all. Okay. Before I begin, I guess I have to do my traditional thing and ask the one fundamental question. The only thing I actually care about today's session is everyone here today fully aware that there's an international salute to mathematics? Did you know there's a math salute? That's what I want to know. And I wish I could see your face. I guess I don't have the gallery view in Remo. Okay, so I assume you're all saying no. So some people are typing yes in the chat. But I'm going to teach the International Math Salute right now because we need to celebrate the end of this fabulous week with the salute to the joy of mathematics. And it goes as follows. It's somewhat strange, so watch out. So you need your arms completely free. So like pens, papers, coffee mugs, sodas, whatever you're holding has to be down. You need your arms completely free. And we're going to do it together as follows. This salute, the salute to mathematics, begins this way. Put your arms out front and make your hands look really big on camera. All right. Then you go right hand over left hand. That's the hard part, right over left. I'll go to a slight angle. Maybe you can see me better that way. All right. Then you go palm to palm. And then the salute gets weird. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, you just come on back. Whoa. Did you catch that? Let me do it again. I'll do it from a different angle. Okay, arms out front. Right hand over left hand. So you really see is my right hand over this left hand, lest this program reverses my image. But right over left, palm to palm, wiggle the little fingers, wiggle the thumbs, wiggle the little fingers again. And when you're ready, just come on back. Ha 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 ha. So how's it going? I can't see your faces, but can you type yes or no into chat? Can I see if it's a yes, I can do it, or no, I'm just befuddled. What is going on? Well, yes, nope, yes, nope. I definitely can't. Befuddled. Someone even wrote the word befuddled. Good for you. Nope, question mark. Okay. Here's what I'll do then. Since we've got answers of yeses and nos, I will half help out people. What I'll do is actually say, this is a salute. I started doing the salute, I guess, about 15 years ago. It's just a playground trick. It's been around for decades, I'm sure. So it's one of those things that's out there in folklore. But I was teaching high school in a school in Boston, and I made this the school salute. So the idea was that at the school assemblies, I would come up with the school salute. It was the St. Mark's School salute. But then it sort of caught on, became like, got a bit of a state reputation and national reputation, the salute. So it became the national salute for a while. And as my life, it was about more traveling overseas and all the rest. Of course, I do this everywhere. It's now become the International Math Salute. And actually, if you Google International Math Salute, you'll see this out and about the place. All right, but let me help out. As a teacher, it actually has a really good maths lesson to this, because I've given you a problem. Often maths is always full of problems, they say. So I've given you a problem. But the thing is, you know what the final answer is meant to be. So if you're given a math problem and you know what the answer is meant to be, or at least can have a good feel for what the answer could be, there's a very simple but extraordinarily powerful strategy in mathematics that you can employ to try to solve the problem. Namely, work backwards. It is so simple, this idea, that people forget to actually do it, but it's a very common strategy in math research. Start with the answer and work backwards. So let me help you out with this math salute. In fact, I'll just half help you out because I've half yeses and half nos. We'll go as follows. So you say yourself, okay, this math salute, I know what the answer is meant to be. The final answer was this, a nice untangled state. So the question is, can I reverse engineer this? So we'll try doing this backwards. So we'll So where must this have come from, you ask yourself? You say, well, it must have come from a twisty motion like that. And then you say, where did that come from? You say, okay, that must have come from clasping my fingers. So here I am, palm to palm. And now you're in this like funny feeling middle position. So you just learned something. I bet that feels very different from what you first did. So we start at the end and we got to this funny feeling middle position. So here's my half a hint for the day. Now you know what it's meant to feel like in the middle. Can you now start at the beginning and somehow get to that same funny feeling middle position? So that's the challenge. That's the challenge. So here's my piece of advice. While I'm being particularly boring for the next 50 minutes about talking what I'm meant to be talking about today, you can just amuse yourselves and just do this off to the side. That I can't see you, so you can do whatever you want and be grand. So here's a way to keep yourself entertained. But if this is driving you really bonkers and batty, at the end of today, please just type in the chat a question, show me the rest of the salute, and I'll give it away because I'm in that mood. I'm feeling very generous today. I'll give it completely away for you. All right. So today, I want to do pile splitting. So that means I need to share my screen. So let's see if this is going to work out beautifully. I'm hoping for the best. Okay, I want to do a strange game. I've got a pile of 9 pebbles, and I want to do some weird mathematics with them. And here's the weird mathematics I'd like to do with these 9 pebbles. It's going to be very strange. Why do I want to do this? I do not know. I'm just doing it. I'm going to start by splitting these pebbles into 2 piles, and I might do, I don't know, random pile of 5 and a pile of 4. Okay, hopefully you can see that now. And on the side, for the fun of it, I'm going to write the fraction 1/5 and 1/4 for a pile of 5 and a pile of 4. And I'm going to add those fractions together because why not? Oh, here's the hard part, arithmetic. 1/5 plus 1/4. That is what? 4/20 plus 5/20. That makes 9/20. So I did my first split, and I've got the fraction 9/20. And hopefully this now showed. Okay, great. Okay, but now I'm going to do it again because now I've got 2 piles. I've got a 5 pile and a 4 pile. I'll choose one of them. Maybe I'll choose the 4 pile and split it into 2, maybe a 1 and a 3. And you can guess I'm going to now write the fraction 1/1 and 1/3 and add them together. And I'll wait for the screen to catch up because it looks very slow on my end. And what is 1/1 plus 1/3? That's 4/3. All right, good way to practice fraction arithmetic, apparently. All right, I'm going to do it again. Split another pile. Maybe I'll split the 5 into a 4 and a 1. I'm just choosing random numbers there. And I'll write 1/1 plus 1/4, and that makes 5/4. Why am I doing this? I don't know. I'm just having fun. Can I split again? Yes. Maybe I'll do the 4 into a 2 and a 2. 1 tooth plus 1 tooth equals 1. Can I split again? Yes. A 2 can go into a 1 and a 1. Where's the screen? Hurry up, screen. There we go. Okay, well, this is one of the most interesting math talks ever. But here's the freaky thing. This time I've got all these crazy numbers. Now I'm going to add them up. Rather than multiply them, I'm going to add them. So clear my screen, and I'm going to add up these numbers. This 1, 2, 3, 4, 4, 3, 2, 1, plus this 1, 2, 2, 1, plus this 11, 11, plus this 1, 1, that's 2, plus this 1, 1, 1, 1, 1, 1, plus this 11, 11, plus this 1, whoops, 1, equals 1, 2, 3, 4, 5, 6, 7, 8. That is suspiciously nice. Whoa, 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 your turn. Start with, say, a small number. Let's all do 5 pebbles. 5. Split it any way you like. Someone show me with their fingers on screen how you like me to split that. 2 and a 3. So it's going to be a 1, 1 times a 1, 1, 1. I'd like you to keep doing that. Work out all these products and then add them up and tell me what number you get in chat. Keep going, and what do you get? Okay, people are writing in chat. Oh, 3 people have done it already. They're fast, and they got the same answer. Anyone else? Oh, more people are getting The same answer.
I have a quick question. What would happen if you did digit sums?
Digit sums, good question. We should do that next. I wonder, but that's so suspicious. This is like the same. Everyone's getting 1, 2, 3, 4. So I guess the digit sums would be the same as well, which would be really interesting. Digit sums. Hold on to that thought because I think you're onto something, clever fellow. All right, I like that idea. Digit sums, I will do them. For those that might be wondering, I'm doing variations of a puzzle that's out there. It's been around for decades. Most people do it this way. They don't do what I've been doing with crazy fractions. They don't do what I normally do with all these ones. They do the following. Again, take 9 pebbles and split them any way you like, 2 and 7 say. But this time, just write 2 times 7 is 14 on the side. And split the 2 into 1 and 1, you get 1 times 1 is 1. In fact, you keep doing this. In fact, keep doing it. Write down your own tree and then get these different products and add them all up. What number do you get? Here's a third variation in this crazy day, in this crazy end of the week. And there's definitely different choices you can make along the way. I'm going to choose 2 and 5 because I know that's 10 and I multiply them. All right, how are we in the chat? What sort of answer are people getting when you add up all these products in the end? Someone got 36, someone else got 36, someone else got 36, someone else got 9.
You get 9. You get 9 if you do the digit sum.
I was guessing you were doing the digit sums. I knew it. I knew that was the digit sum. Okay, you get 9, which is the original number of pebbles. Oh my goodness, that would be so freaky. But everyone else is getting 36. 36. What did I get? I got 15, 25, 26, 32 plus 4. I got 36 as well. Everyone's getting 36. All right, all right. So I guess the real question is, what is going on? What is happening here? Why are we all getting the same number of 1, 2, 3, 4 when we're doing with 5 pebbles and the ones? We're getting the same digit every time when we do the crazy fractions. And why is everyone getting the number 36 for these weird product things? And there's still lots of crazy echoes again. And there's a time delay. Some people, not for everyone. Okay, Beth, I'm afraid this is something special for you. I'm so sorry. Oh my goodness, what a crazy day. What can I do about the echoes? What if I paused, muted myself and unmuted again?
Oh, Beth, I think the issue is actually that you might have the old Remo tab open. I currently have the live stream going through Remo for the people who weren't able to move over. So I think Beth just needs to close out of that. So if you're having any kind of echoes, it's because you're looking through multiple feeds of James. Sorry about that.
Which is a fine thing. Feel free to view me in many ways at once. So that could be charming. Well, probably not, probably more scary. All right, okay. So what is going on? So since this is a classic puzzle, maybe someone's seen this version. I'm going to give you the classic answer to this puzzle, what people tend to do. So this one will always be 36. No matter how you split this up, these sums will always be 36. And let me show you why. Let me show you why in the classic textbook where I'm giving away the answer right now. So the idea is that imagine that you put your pebbles in a circle. Okay, why not? And that imagine that there's like rubber bands or strings of rubber connecting each and every pebble in pairs. So for example, this pebble is connected to each of its 8 friends. And this pebble is already connected to that one, but it's also connected to 8 of its each other friends. Oops. Okay, I guess they're elastic, they can bend. And this one's also connected to all of its other friends. And this one's connected to all its other friends. And this one's connected with all its friends. And this one's connected to all its other friends. And you get a really crazy picture of all these rubber bands connecting all the pebbles. All right, is that a good enough picture? Just say yes, or just nod, or just be polite and say nothing. All right, but here's my first question. If every pair of pebbles is connected with a rubber string, how many strings are there? And I kind of started giving the answer away when I was just having.
Yeah, you have
Eight.
9, 8, 7, 6, 5, 4, 3,
Yes.
and you start all.
This one was connected to 8 other friends, right? That's the first one I did. And then you notice I said, oh, this one's already connected. So that string's already counted. It's connected to 7 other new friends. And this one's already connected to this one and already connected to this one because they've already been connected to its friends. So it's connected to 6 other friends. This one's connected to, well, it's connected to all those ones already. It's connected to 5 other friends, 4 new rubber bands, 3 new rubber bands, 2 new rubber bands, 1 new rubber band. And this one would already be connected to this because all these guys are already connected. This one needs no other rubber bands to connect it. So actually the total number of rubber bands is 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. And what is 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1? What number is that? It's that 36. All right, now, how does splitting this pile of 9 pebbles somehow got something to do with 36 rubber bands? And people say, well, okay, imagine you did what you did, James Tanton, when you went 5 and 4. Let's pull these pebbles apart into 4 over there and 5 over there. And imagine your rubber bands aren't very good. They get stretched too far, they break. For example, this string here that connected this rubber band to that rubber band got pulled too far, it broke. And you can't see that because it's a really bad marker for the camera. Try this one. This band here between those 2 pebbles stretched too far and went snap. This rubber band that connected this one to this one got stretched too far, it went snap. This one over here between those 2 didn't snap, it's fine. In fact, though all these ones here amongst themselves are fine. They didn't snap. These ones didn't snap amongst themselves, but every one that connected from the left to the right snapped. So here's my first question. When I split into 5 and 4, how many rubber bands snapped? Okay, someone mimed. Right, 5 times 4. I love this. This is like math by all technologies. Mime, voice, microphone, Zoom, remote, everything. Yes, think about it. Because each of these beads over here is got 4 rubber bands coming to a faraway friend. So there's one group of 4 that got snapped. From this one, there's another group of 4 that got snapped. From this one, another group of 4 got snapped. From this one, another group of 4 got snapped. From this one, another group of 4 got snapped. 5 times 4 rubber bands got snapped. And then when I split again, if I split this and say just 3 and 2, oh, some more snappage will be occurring. How many rubber bands got snapped then? Well, this is connected to 2 other pebbles, 2 other pebbles, 2 other pebbles, 3 groups of 2 bands, 3 times 2 rubber bands snapped. And then here, how many rubber bands snap? You can't see it, there it goes. 1, 2 rubber bands snap. 1 times 2 rubber bands snapped. 1 times 1 snapped. 1 times 1 snapped. 2 times 2 snapped. 1 times 1 snapped. 1 times 1 snapped. So when I finally stopped, every rubber band snapped. All 36 rubber bands snapped. Now I separate them into 9 piles of 1. Every single rubber band snapped. But first I snapped this many, then I snapped that many, then I snapped that many, then I snapped that many, snapped that many, snap, 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 snap. All these products must add up to the total number of rubber bands that got snapped. Therefore, when I play this game of counting up all these products, these are just counting up how many rubber bands get snapped as I play the game, and it must be all 36 of them. No matter what you do, it'll be 36 rubber bands get snapped, which is lovely, But it doesn't explain my crazy fractions or my crazy ones or anything else. It doesn't. So what's going on? What's really going on?
And also, where do digit sums come into that?
And the digit sums. Benjamin wants me to talk about digit sums. I will definitely talk about digit sums. All right. But let me just help out the rest of the world with digit sums to make sure everyone knows what that means. For example, well, I think we have to do 9. I'll do yet another example of 9. I'll do 8 and 1, and I'll do, say, 4 and 4, and, oh, guess the one's done. I'll do 3 and 1, and a 2 and a 2, and a 2 and a 1, and a 1 and a 1, and a 1 and a 1, and a 1 and a 1. I think that's everything. Is that right? Okay. 8 times 1 is 8. 4 times 4 is 16. 3 times 1 is 3. 2 times 2 is 4. Now you can see what my handwriting is truly like in real life. 2 times 2 is 2. 2 times 1 is 2. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. First of all, I do notice something else before I get to digit sums. 1 split, 2 splits, 3 splits, 4 splits, 5 splits, 6 splits, 7 splits, 8 splits. I don't know if you've noticed, every single time we played this game, 1 split, 2 splits, 3 splits, 4 splits, 5 splits, 6 splits, 7 splits, 8 splits again. The number of splits with 9 pebbles is always 8. Can anyone see a reason why that's true? Why would the number of splits have to be 8 every time? And I bet if you look back at your scrappy pieces of paper, it was 8 every time. That's, oh my God, okay, there's a mystery before I get back to digit sums and other things. Whoa, this just keeps unfolding into more mysteries. Why would 9 pebbles always have to be 8 splits no matter what you do? All right, now if I was a good math teacher, which I'm not going to be a good math teacher today, I'd like, let's go into our breakout rooms, let's all think about it together and have a great time chatting with each other. But we're not going to be social today. I'm going to take the floor and just be my bad teaching self. And people have written things in chat. Okay, people have ideas. Oh, okay, people have lots of ideas. Okay, so we don't need to chat because people are actually chatting in the chat window. Yes, people are saying this sort of thing. Imagine I lined these up in a row. Instead of doing a circle of 9 pebbles, I'll do a line of 9 pebbles this time. And every time I make a split, it's really doing the following. It's like I grab my ruler, I happen to have one, I go split. That is, I put 5 on one side and 4 on the other side. That is, I put a line here and made a split. And then when I do a split later on, maybe I'll split the 5, I'll put my ruler there. I'm going to make a split there into a 2 and a 3, which means I split there. In fact, every split I do is just putting a line between a space between 2 pebbles. There's a pile of 3, I'm going to split into a 1 and 2. There's a pile of 3 and split into a 2 and a 1. There's a pile of 2 split into a 1 and a 1, a 1 and a 1, a 1 and a 1. And oh, that's it, and that's it. In fact, every split I do corresponds to drawing a line in between 2 pebbles. The question is, how many spaces are there between 2 pebbles? Hint. 8 of them. There are 8 spaces between 9 pebbles. Therefore, there must be 8 splits no matter what you do. Okay. Let's get freaky here. I'm full of more mystery than I am answers today. Look at this. There's an odd pair, an odd number and an odd number. There's an odd pair, 1 and a 1. There's an odd pair, 1 and a 1. There's an odd pair, a 1 and a 1. That's 4 odd pairs. I bet every example you did, you also have 4 odd pairs. See if you pull out a past piece of paper. Circle the ones that have pairs that have both odd numbers odd. Four of them every time. Can anyone explain why the number of odd pairs always has to be 4? Half the 8. Huh. And by the way, the answer can be no. That was technically a yes/no question.
Is it because there's only the 4 odd numbers?
Oh, the 4 odd numbers we work with are 1, 3, 5, and 7. That's interesting. And 7 didn't appear anywhere in this one. I don't know if that's a concern or not. Yes, there are 4 odd numbers. What that makes then 4 odd pairs? Could be something to that. All right. I have a question for everyone. How are we feeling right now? Are we brain tired from a fabulous week of deep maths, and we want James Tanton to just give it all away? Or would you like to keep thinking about this? Or shall I be an obnoxious person? There's some deep thought to think about. Go think about it. Have a happy life. Would you like me to give things away? Would you like me to reveal how my brain works on these sorts of things? Which I was just, yes, yes. Okay, 2 people answered yes. They're speaking on behalf of everyone. Give it away. Yes. You know, I'll tell you one thing. There's only a couple of things in my life that I feel like I've done mathematically that I'm proud of. And I think it's this one is one of the things, because I don't know why. I saw this little puzzle and saw it being explained about pulling out rubber bands. I said, that's very cute, but it feels very specific for that one example. There's got to be another way to think about this. And I spent probably weeks just mulling on this, waiting for another way to think about it. This is why I think it's unfair for me to do this with you today when we've got 15 minutes left, and for you to do what took me weeks, because you're cleverer than me, but what took me weeks probably still take, you know, like an hour for you guys. Let me just give it away in 15 minutes. I had this epiphany. That I said, okay, I don't know what my brain did, but here's the best thing about being a mathematician. The best way to solve a math problem is to read the problem, have an emotional reaction, cry for a little bit because it's scary and hard, or whatever your emotional reactions could be, like, I'm delighted, this is intriguing, but I don't know what to do. And then take a deep breath and do something. And the best do something there is to a math problem that's hard is to let it go and go for a walk and go do something else for a while. Let your subconscious work on it. They don't teach you this in school, because everything in school is about do it now, do it now, do it now, do it now, which is not how maths work. But this is what happened to me. When I was doing this as a mathematician, just had the freedom to do this, I came up with the following crazy idea. I can't explain where it came from, what made me think of it, but it's obviously my brain had been working on this for weeks, trying different ideas until I finally hit upon the one thing that clicked for my brain. There's probably better ways to think about it than my brain, but I know there's probably better ways. But here's the idea I had. I said, okay, before you do anything, just write down any sequence you like, any sequence of numbers. I'll call them A1, A2, A3, A4, A5, a sixth one, and so on. Just write down any sequence of numbers you like. For example, they could be the Fibonacci numbers. First one is 1, the second one is 1, next one is 2, 3, 5, 8. They could be the square numbers, 1, 4, 9, 16, 25, 36. Or they could be the prime numbers, 2, 3, 5, 7, 11, 13, whatever the sequence of numbers. Just write down a sequence of numbers. And I said to myself, okay. Every time you do a split, you've got some number of pebbles that splits in, say, B and C. That means B pebbles and C pebbles must add up to A pebbles. Write down on the side the Bth number in your sequence plus the Cth number in your sequence, these two, minus the top number of the sequence, which is the, what, B plus C. So A is the same as B plus C. Just write that down. Write that down. And then when you split it again, maybe it splits into a D and an E, just write down the same thing for that. It'll be the D and the E and their sum, which is the B. And do that over and over and over again. Now, the reason somehow my brain saw some pattern in that, and here's the pattern I saw. I wrote this up earlier because I actually did it with an actual example. So I imagine I had a sequence in my mind, and I split this way. And when I did the 5 and the 4, I wrote, okay, the 5th number in my sequence plus the 4th number of the sequence, take away the top number in my sequence. And I did the 5 was the 2 and the 3. 2 plus 3 minus the 5. And I did the 1 and the 3 and minus the 4. And I did the 1 and the 1 minus the 2. And the 2 and the 1 minus the 3. And the 2 and the 1 and the minus the 3. And the 1 and the 1 minus the 2. And the 1 and the 1 minus the 2. There's all 8 splits. And then look what happens if you add these up. Add up all these numbers. For example, here's a 5th number in the sequence as a positive term, but it later got subtracted. So that cancels out. The 4s cancel out. In fact, every number in the middle gets used at the top and the bottom. This is part of the A2 plus A3. Where's the A2 plus A3? There it is. But then it also gets later used as the 2 and the 1 take away. Where's the 2 and the 1 take away? So that A3 gets cancelled. In fact, all these middle terms will get cancelled out. In fact, all the 2s cancel out. Where's another one? There's an A3 and another A3. There's an A2 and another A2. There's another A2 and another A2. And all I'm left with is the very top number, which gets subtracted away but never got used again. And I get all the bottom numbers, the 1s, that never get used again, only get used once. So what I'm left with is all the A1s. If I'm left with 9 A1s and take away the A9 at the top. Everything in the middle just disappears or cancel out. So it doesn't matter what I do in the middle. All that matters is the 9 ones at the end and the 9 at the beginning. You will always get this answer. And I said, wow, that's what's really going on. Everything cancels in the middle cancels. So all I have to do now is just choose my favorite sequences and I'll get some crazy answers here. So for example, let me choose a really interesting sequence. I'll choose the square numbers. So I'm going to assume we know some high school maths now because I'm going to do some high school maths. That is, I'm going to let A of n, the nth number, bn squared. And when I was splitting into a b and a c, what I would write down is the bth number plus the cth number minus the top number, b plus c. All I have to do is work out what that is. Okay, well, that's really b squared plus c squared. And that a is really b plus c, so it's really b plus c squared. Okay, great. Let me do some algebra on this. That's a b squared plus a c squared minus a b squared plus a c squared minus plus a 2bc. Ooh, b squared take away b squared, c squared take away c squared. That gives me negative 2bc. Ooh, I don't want negative 2, because what I was doing, if you remember, my very first one was just multiply b and c and just write down b times c. So I'm going to be a little bit sneaky. Go back. No, I don't want n squared. I want negative a half n squared, negative a half, 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 half, negative a half times that, b times c. By playing with this sequence and writing down the products, the sum always has to be this invariant. That sequence, writing down the products as you split terms, recording the products, add them all up, you always get the same answer in the end. And for 9, it turns out to be 36. Whoa. Whoa. Okay. Can I keep going? Can I keep going? Because I'm just revealing to you how my brain works. This is today is like lecturing now. I'm now revealing. Because then I started getting crazy with choosing different sequences. Another one I chose was this one. A of n equals 1. It's always 1. No matter what it is, the nth term of the sequence is 1. The first term is 1. The second term is 1. The third term is 1. The 100th term is 1. The 1000th term is 1. The 944,226,644 and 2th one is 1. Not a very exciting sequence. But the idea was whenever I'm splitting a pile, I write down this number. A, the bth term, the cth term, take away the top term, b plus c, which would be 1 plus 1, take away 1, is 1. So every time I do a split, I just write down the number 1. Do a split, 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 write down the number 1. And then I add them up, and I will get n a1s minus a of n, which is n times 1 minus 1. Remember, with 9 pebbles, we always got 8 splits. There's a general formula. All right, Benjamin, I want to know what sequence I should use to prove your digit sum result. What clever choice should I use there at the top? There's got to be one, but that's now your challenge. What would be the right sequence to choose to get your digit sum result?
I'm thinking, I sort of like the mark sequence.
Okay, then play with it, see, because I bet it's going to give you something interesting. But I'll show you how crazy I got. I started doing things like this. A of n is a half if n is odd, and it's 0 if n is even. Whoa, whoa, I got really crazy. So I started doing split things. When it's n, it's one value. When it's odd, it's another value. Because then when I did a split, because I realized, you see that half is suspicious. Why did I do a half? Because obviously I did something easier first and realized, oh, I'm off by a factor of 2. I would write a of b plus a of c minus a of b plus c. And if you check it, if both b and c are even, like I had an even pair, I'd get 0, 0 minus 0, it'll be 0. If one of them is even and one of them is odd, like b is even and c is odd, I'd get 0 plus a half minus, well, that'll be odd as well, a half, it'll be 0 again. But the only time it's not 0 is if both b and c are odd and it has the value 1. In which case, if I have an odd pair, I get 1 and I get 0 otherwise. This just counts the number of odd pairs. And you're right, it turns out to match the number of odd numbers up to 9. So your intuition is absolutely on the mark. Absolutely on the mark. Do you want to see how I did the crazy ones? We have 6 minutes left. The answer is yes, because I'm the one speaking and I'm in lecture mode now. I'm being a terrible math professor. I'm just telling you all the answers and I'm not giving you any room to think for yourself. So, okay, here's my crazy ones. This is so not math circle-ish. Do not conduct a math circle this way. I'm ending off the week by showing you how not to do math circles. How's that? This is the counterexample. You always should have examples of what things do work and examples of things that don't work, so you know what not to do as well. The crazy ones. All right. I chose an insane sequence. You're not going to like it. The nth term of my sequence is negative 1/81th of 10 to the n minus 1. Now, obviously, my brain is not that clever. I must have thought about this for a long while and said, why am I putting in a factor of negative 1/81th? That is crazy. That is insane. So let me try to reveal to you what my brain was doing when I came up with that thing. Obviously, I didn't come up with that cold. I wrote something down. It was bad. I kept adjusting. And about a week later, I came up with that. All right, here's what my brain was thinking. If I take the number, say, 10 to the 9th minus 1, that'll be 1 with what, 9 zeros? Take away 1, which would be 999,999,999. It'll be the number with 9 nines. In fact, 10 to the n minus 1 would be the number 9999 with n nines. Ah, then that makes me think, oh, 10 to the n minus 1 divided by 9 would be the number 11111 with n ones, 1/9 of that. So obviously I was shooting for something that kept giving me that. I wanted to go for that, something in my brain, say, how can I find a sequence that in the end will give me that? And turns out that is the correct thing. And let me show you how. Let me show you how. Oh, I'm running out of pages. What am I going to do? What am I going to do? I don't know what I'm going to do. I'm going to take that away and remember it. So the nth term was negative 1/81th, 10 to the n minus 1. And every time I do a split a pile of A pebbles into B and C pebbles, I would write down this number, A of B plus A of C minus A, the top one, which is B plus C. And then about 4 hours of algebra later, which we shall now do because we've got 4 minutes, we'll work this out. We'll work this out. It's crazy. Negative 1/81th, 10 to the B minus 1. And negative 1/81th, 10 to the C minus 1. And negative 1/81th, so that's positive 1/81th, 10 to the B plus C minus 1. Doesn't this look great? By the way, I've written all this up for you. I'll share a PDF with you on all this stuff. Don't bother trying to take notes. Just don't bother. It'd be horrible. Don't take notes. No. Just live in the moment and say, wow, that's cool. I don't have a clue what happened just then. And then you can look at the notes if you want to, or you just like run away screaming and never look at this stuff again. So I'll give a URL to all the notes after this. All right, but here goes. I've got all these 81ths. Okay, let me pull out a common factor of 81ths. My brain can't handle that. All right, I've got this one. I've got 10 to the B plus C minus a 1. I've got a negative 10 to the B minus 1, so negative 10 to the B plus 1, and a negative 10 to the C minus 1 plus 1. Okay. Negative 1 plus 1. Okay, great. 1/81th, 10 to the B plus C minus 10 to the B minus 10 to the C plus 1. Okay, people cleverer than me can do this sort of thing all the time. People are really good at factoring. I'm lousy at factoring. But it took me forever to realize that this is actually 1/81th times 10 to the B minus 1 times 10 to the C minus 1. Actually, if you work backwards, you see it's true. I like working backwards. If I start with the answer, 10 to the B times 10 to the C is 10 to the B plus C, minus the 10 to the B, minus the 10 to the C, minus 1 to 9 is plus 1. Yes. Okay. And now you see why I wanted 81ths, because I could rewrite this, okay, really bad paper technique. So I'm being not only just a bad math circle piece, I'm being a really bad math teacher in general. This equals 10 to the B minus 1 over 9 times 10 to the C minus 1 over 9, which is a product of ones times a product of ones. That's the crazy ones. That's really 1, 1, 1, 1, 1, 1. And that's really 1, 1, 1, 1, 1. There's B of them. Oops, you can't see that. There's C of them, and you multiply them together. If you add them all up, you will get the same answer in the end. Whoa. Okay. So bad technique, but here's what I'm going to do for you. We now have 2 pieces of homework. One is, if you don't want to do any work and you still want to see what's going on, here's the website, jamestanton.com/P equals 2350. I'm not very good at making that simpler, but there it is. I do have a website with my name on it, but I wrote up a document that explains all this maths and more, if you want to just look that up. I also have 2 videos there of me doing some of this stuff, so you can look at the videos too if you want, just for fun. That's piece number homework. Here's the look it up homework if you want. All right. Then the special Benjamin homework. What about digit sums? Maybe there's like a sequence way to think about that, or maybe there's just a clever way to think about, like just putting rulers between lined up dots. And then there's the crazy fractions. I didn't get to crazy fractions. Why are they working? And now we're different, actually. If you notice them, I wasn't adding up all the numbers. I was multiplying all the numbers that time. So the crazy fractions are interesting. What's going on with those? And the only thing I actually care about today, are you okay with the math salute? Have you been secretly practicing this all along? That's the real question for today. So now I see the hour has turned. I'm going to stop right there, except I want to end off with a final salute to mathematics to end this spectacular week that we've been flitting in and out of all week. And I bet some of you have been there for all 168 hours of it. So to end off today, to say thank you for putting up with this very strange math circle session with me today, here's the final salute to mathematics and the joy of mathematics. Arms out front. Oh, I can do gallery view. I can watch you all this time. I'm watching. Stop sharing my screen. I'm going to watch you. Okay, this is serious now. Now I can see you. This is fabulous. Arms out front. Yes. Right hand over left hand. That's the hard part. Yes. Palm to palm. Looking good. Looking good. Wiggle the little fingers. Wiggle the thumbs. Wiggle the little fingers again. And when you're ready, just wait for it. Come on back. Excellent. Good job, guys. Thank you so much. Thank you, everyone.